Imagine for a moment that gravity, the force we've been taught is a fundamental pillar of the universe since the days of Newton and Einstein, isn't actually a primary force at all. Instead, what if it's just a byproduct, a secondary shaking caused by the intense quantum fluctuations of the vacuum? It sounds like science fiction, but this idea, known as the Sakharov hypothesis, suggests that gravity is more like the static cling of the universe than a dedicated force field. Today, we're diving into a landmark 1989 paper by Hal Puthoff titled Gravity as a Zero Point Fluctuation Force, where he attempts to prove that Newton's law of gravitation can be derived entirely from the electromagnetic jitters of empty space. Imagine for a moment that gravity, the force we've been taught is a fundamental pillar of the universe since the days of Newton and Einstein, isn't actually a primary force at all. Instead, what if it's just a byproduct, a secondary shaking caused by the intense quantum fluctuations of the vacuum? It sounds like science fiction, but this idea, known as the Sakharov hypothesis, suggests that gravity is more like the static cling of the universe than a dedicated force field. Today, we're diving into a landmark 1989 paper by Hal Puthoff titled Gravity as a Zero Point Fluctuation Force, where he attempts to prove that Newton's law of gravitation can be derived entirely from the electromagnetic jitters of empty space.
It's a radical shift in perspective. To understand Puthoff's work, we have to start with the concept of the zero-point field, or ZPF. In classical physics, a vacuum is empty. But in quantum mechanics, thanks to the uncertainty principle, empty space is actually teeming with energy. Even at absolute zero, fields are constantly fluctuating. Puthoff's paper builds on the work of Andrei Sakharov, who, in 1967, proposed that gravity isn't a fundamental interaction like electromagnetism, but an induced effect. Sakharov compared it to the elasticity of a solid. When you push on it, the resistance isn't a new force, it's just the collective behavior of the atoms inside. Puthoff takes this further by providing a specific electromagnetic model to show how this actually happens at the particle level.
So instead of a graviton particle or a curved fabric of spacetime being the starting point, he's starting with light, or at least electromagnetic waves. But if gravity is just a side effect of electromagnetism, why don't we see magnets falling faster than rocks? Why is gravity so much weaker than the electrical forces holding our atoms together?
That's exactly what the paper addresses. Puthoff uses a framework called stochastic electrodynamics, or SED. It's a way of looking at quantum phenomena using classical equations, but adding in this background of random zero-point radiation. He models matter as partons, charged point particles that are constantly being buffeted by these fluctuations. He calls this motion Zitterbewegung, a German term for a trembling motion. This isn't just a metaphor. According to the paper, this constant jittering is actually where mass comes from. He argues that what we perceive as the rest mass of a particle is really just the internal kinetic energy of its response to the ZPF.
Wait, so he's saying that if we could somehow turn off the vacuum fluctuations, particles would be weightless? That the very stuff of matter, its mass, is just energy borrowed from the background noise of the universe?
In this model, yes, Puthoff derives the relationship where mass equals the kinetic energy of this Zitterbewegung motion. This is a crucial first step because in standard physics, mass is usually just a given parameter you plug into an equation. Here, it emerges from the dynamics. He references a 1952 paper by K. Huang and the work of Alfonso Rueda to show that this internal motion reaches a finite magnitude because the ZPF spectrum has a cutoff frequency. Without a cutoff, the energy would be infinite, which obviously isn't what we see. He identifies this cutoff as the Planck frequency, which is incredibly high, around 10 to the 43rd power hertz.
Okay, so the jittering gives us mass, but how does that jittering turn into an attractive force between two separate objects? If two things are both shaking randomly, wouldn't they just stay apart or bump into each other?
This is where the van der Waals force comes in. Most of us learn about van der Waals forces in chemistry as the weak attraction between molecules. It happens because even neutral atoms have fluctuating dipoles. Their electrons shift, creating tiny, temporary positive and negative ends. These dipoles then synchronize with the dipoles of neighboring atoms, creating an attraction. Puthoff argues that gravity is essentially a long-range version of this. When those partons jitter in the ZPF, they act like oscillating dipoles. They generate their own tiny secondary electromagnetic fields. When you have two particles, their Zitterbewegung becomes slightly correlated because they are both responding to the same background ZPF and to each other's secondary fields.
So it's like two people dancing on a vibrating floor. Even if they aren't trying to move toward each other, the way they react to the floor's vibrations and the way their movements slightly change the floor's vibration for the other person eventually draws them together?
That's a great analogy. Puthoff calculates the potential of this interaction and finds that at large distances it follows a 1/r relationship, which is exactly the mathematical form of Newton's law. What's really striking is that he doesn't just get the shape of gravity, he gets the magnitude. By using the equivalence principle, the idea that being in a gravitational field is indistinguishable from being in an accelerated frame, he links the ZPF spectrum seen by an accelerating observer to the field generated by a mass. Through this, he calculates the gravitational constant g. He finds that g is proportional to the inverse square of that Planck cutoff frequency. This explains why gravity is so weak, because the ZPF energy density is so incredibly high, the resulting residue force is tiny.
I noticed he mentions that this theory is already unified. That's a bold claim considering physicists have been struggling for a century to reconcile gravity with the other three fundamental forces. If he's right, does that mean we've been looking for the wrong thing? We've been trying to quantize gravity, but he's saying gravity is just a side effect of a field that's already quantized.
Precisely. If gravity is an induced effect of the electromagnetic field, then you don't need a separate quantum gravity theory. You've already unified them by showing one is a manifestation of the other. Puthoff points out that if this model is correct, attempting to quantize gravity as a separate field is a mistake. It would be like trying to find the atoms of elasticity instead of looking at the atoms of the material itself. This approach also explains why gravity can't be shielded. Ordinary electromagnetic fields can be blocked by conductors because the electrons in the conductor move to cancel the field. But you can't shield the ZPF. It's everywhere at all frequencies. Since gravity is driven by this universal noise, there's no way to put a screen between two masses to stop the attraction.
It sounds very elegant, but I have to play devil's advocate here. If gravity is just electromagnetism, why don't neutral objects like the Earth and the Moon repel each other? Electromagnetism is usually about both attraction and repulsion. Why is gravity always attractive?
That's a classic challenge. In Puthoff's model, the attraction stems from the fact that the kinetic energy of the Zitterbewegung is always positive. When he calculates the interaction potential, specifically looking at the long-range radiation fields rather than the short-range induction fields, the math consistently yields an attractive 1/r² force. The charge in this case isn't the electric charge of the particle, which can be positive or negative, but the mass, which is derived from the square of the motion. Since you can't have negative kinetic energy in this classical sense, you don't get negative mass or repulsive gravity in this framework.
What about the finer details? Puthoff mentions something called a fine structure overlay in the gravitational potential. He says there's a spatial periodicity based on the Planck wavelength. That sounds like something we should be able to measure, right? If the force of gravity wobbles slightly every 10 to the minus 33 centimeters?
He does mention that. The potential isn't just a smooth curve, it's modulated by a term involving a sine function squared. However, the period of that oscillation is the Planck length, which is many orders of magnitude smaller than anything we can measure today. At our macroscopic scale, or even at the scale of an atom, we only experience the average force. In Appendix B of the paper, Puthoff goes through the math of averaging this rapidly varying component over a distance. He shows that the wiggles cancel out, leaving us with the smooth inverse square law we see in textbooks. It's essentially invisible to modern instruments, but it's a fascinating theoretical prediction.
One thing that puzzles me is how this handles the vacuum catastrophe. If the ZPF has as much energy as Puthoff suggests, enough to create the force of gravity, wouldn't the weight of that vacuum energy itself be enough to curl up the entire universe into a tiny ball? This is a huge problem in cosmology, where the predicted vacuum energy is 120 orders of magnitude larger than what we observe.
This is actually one of the strongest points of the Sakharov-Puthoff approach. In standard general relativity, all energy, including the energy of the vacuum, must gravitate. This leads to the massive discrepancy you mentioned. But in Puthoff's model, gravity is caused by the interaction of matter with the ZPF. The ZPF itself doesn't gravitate because it's the source of the force, not the subject of it. It's like saying the wind can move a sail, but the wind doesn't blow itself. He explains that the vacuum energy doesn't generate a massive gravitational field because in his dynamics, only the modifications to the ZPF caused by the presence of matter result in a force. This sidesteps the cosmological constant problem by redefining what causes gravity in the first place.
It's a clever way out, but does the paper address things like the bending of light or the slowing of time near a black hole? General relativity isn't just about things falling, it's about the geometry of space itself. Can a van der Waals model explain why a clock runs slower on Earth than in space?
Puthoff admits in the discussion that his 1989 paper is a first-order model. He focuses on the Newtonian limit, the force between masses in flat space-time. However, he argues that this approach is compatible with the broader goals of general relativity. Later researchers in this field have suggested that the refractive index of the vacuum changes near a mass because the ZPF is more concentrated there. If the vacuum itself becomes thicker with fluctuations, light would slow down, which would look exactly like the curvature of space. So while this specific paper doesn't derive the full Einstein field equations, it provides the physical mechanism, the why, behind the geometry.
The paper also spends time on the Zitterbewegung being two-dimensional. He says he models the parton as a two-dimensional oscillator to account for spin. Why is that necessary? Does it change the gravity calculation significantly?
It's a technical detail that ensures the model aligns with quantum observations. Spin is a fundamental property of particles like electrons and quarks. By restricting the jitter to two dimensions, he's able to incorporate the internal angular momentum that we see as spin. Mathematically, it introduces a reduction factor of 2/9 into the coupling constant, which he explains in Appendix A. It's basically him showing that the model is consistent with the internal structure of particles as we understand them in particle physics, not just a generic shaking ball model. He's trying to bridge the gap between high-energy physics and gravity.
It seems he's also trying to solve the problem of mass renormalization. He mentions dressed mass versus bare mass. In standard quantum electrodynamics, you often end up with infinite values that you have to subtract away to get the real-world mass. How does his ZPF model handle that?
He argues that the bare mass, the mass a particle would have without any interaction, is actually much larger, possibly near the Planck mass, but because of the way it interacts with the ZPF, we only observe the dressed mass, which is the internal kinetic energy. It avoids the need for arbitrary subtractions because the observed mass is a direct result of the interaction. It's a more physical way of looking at it. Instead of mass being an intrinsic, mysterious property, it's a dynamic equilibrium. The particle is in a constant dance with the vacuum, and the energy of that dance is what we weigh on a scale.
So, to recap the logic, the vacuum is full of electromagnetic noise called the ZPF. Particles are pushed by this noise, making them tremble. That's Zitterbewegung. This trembling gives them what we call mass. Because these trembling particles are charged, they create their own ripples in the ZPF. When two particles are near each other, their ripples interact, creating a slight universal attraction. That attraction is what we've been calling gravity for the last 400 years.
That's exactly it. It takes gravity out of the realm of fundamental mystery and puts it into the realm of emergent phenomenon. It suggests that the universe is far more interconnected than we realized. Every mass is linked to every other mass, not through some invisible tether, but because they are all swimming in the same energetic ocean. The paper concludes by suggesting that this already unified view might be the most productive way forward, rather than continuing to treat gravity as its own separate, lonely field that refuses to play by the rules of quantum mechanics.
It's a profound shift. Even if the details of the Planck cutoff or the specific parton motions are debated, the core idea that gravity is a byproduct of the vacuum remains one of the most provocative and potentially revolutionary concepts in modern physics. It turns the void of space into the most important stuff in the universe. It makes you wonder what else might be hiding in that zero-point noise.
It certainly does. Puthoff's work invites us to look at the universe not as a collection of isolated objects in an empty room, but as a single dynamic system where even the emptiness is doing the heavy lifting.
What if the reason we haven't reached the stars yet isn't because the distances are too great, but because we're looking at the empty space between them the wrong way? It's a provocative thought. In our standard view of the universe, space is a passive curved stage where matter performs. But there's a radical alternative that's been gaining traction in the more speculative corners of theoretical physics. It suggests that the vacuum isn't just an empty void, but a physical, polarizable medium, one that we might be able to engineer to propel ourselves across the galaxy without needing a single drop of traditional fuel. This is the world of the polarizable vacuum model, or PV for short. At its core, it proposes that we can manipulate the very refractive index of space itself to create a new kind of propulsion. It sounds like science fiction, but the foundations are built on real, albeit controversial, physics. Part 1. The vacuum as a medium. To understand how we might manipulate space, we first have to rethink what space is. In Einstein's general relativity, gravity is the result of the geometry of space and time, the metric, being curved by mass and energy. But the polarizable vacuum model, championed most famously by physicist Hal Puthoff, offers a different interpretation. It draws on work from earlier in the 20th century by Nobel laureate Robert Dicke and H.A. Wilson. They suggested that the effects we attribute to curved spacetime can be perfectly modeled by treating space as a flat medium with variable optical properties. In this view, the vacuum isn't nothingness. It's more like a clear, incredibly dense fluid or a dielectric material. When a massive object like a star is present, it increases the polarizability of the vacuum around it. This effectively changes the vacuum's dielectric constant, which physicists represent with the letter K. Think of K as the refractive index of space. Just as light slows down and bends when it enters a glass lens because of its refractive index, the PV model says light bends near a star because the star has increased the local refractive index of the vacuum. According to this model, near a mass, K is greater than 1. This causes the velocity of light to decrease locally, though we don't notice it because our rulers and clocks, which are also made of atoms interacting with that same vacuum, change their scale in a way that keeps the local measurement of the speed of light constant. It's an ingenious bit of mathematical sleight of hand that reproduces many of the same predictions as Einstein's gravity, but it frames the universe in the language of an engineer rather than a geometer. If gravity is just a change in the vacuum's refractive index, then maybe we don't need a whole star's worth of mass to create those changes. Maybe we can do it with electromagnetic fields. Part 2, metric engineering and propellantless thrust. This is where we get into metric engineering. If the properties of the vacuum, the permittivity and permeability that dictate how electricity and magnetism move, are tied to this K factor, then it might be possible to use high-intensity electromagnetic fields to artificially alter K. Puthoff and his colleagues suggest that by creating a gradient in the vacuum's polarizability, we could generate a force. Imagine a spacecraft that can use powerful fields to make the vacuum in front of it more thin or less polarizable, making K less than 1, while making the vacuum behind it more dense or more polarizable. This would create a pressure differential in the quantum vacuum itself. It's essentially like creating a permanent downhill slope in space that the ship constantly falls into. The beauty of this concept is that it would be propellantless. Conventional rockets work on Newton's third law. You throw mass out the back to push yourself forward. But a PV drive would interact directly with the underlying fabric of space. It wouldn't need to carry massive tanks of fuel. It would just need a powerful enough energy source to keep those fields active. Some theorists have even looked at how this could explain or even realize the famous Alcubierre warp drive. In the PV representation, a warp bubble isn't just a geometric distortion, it's a region where the effective refractive index is engineered so that the effective speed of light inside the bubble is vastly higher than it is outside. This would allow a ship to travel at what looks like superluminal speeds to a distant observer, while never actually breaking the local speed limit within its own little pocket of modified vacuum. Part 3. The challenges and the critics. Now, as exciting as this sounds, we have to look at the massive hurdles. First, there's the energy problem. To make even a tiny, measurable change in the vacuum's refractive index using electromagnetic fields, you would need energy densities that are frankly astronomical. We're talking about field strengths that might only exist in the hearts of stars or near black holes. Our current technology is nowhere near being able to generate those kinds of sustained, localized fields. Then there's the hidden momentum problem. Mainstream physics points out that whenever you try to use static electric and magnetic fields to create momentum, what's sometimes called EXH propulsion, there are often subtle internal mechanical effects that perfectly cancel out any net thrust. It's like trying to push your car forward by sitting in the driver's seat and pushing on the dashboard. Conservation laws are notoriously difficult to bypass. Most importantly, the PV model itself is considered A fringe physics. While it matches the basic tests of general relativity in weak gravity, critics like physicist Matthew Ibison have shown that it starts to fall apart when you look at more extreme cases, like how binary stars lose energy through gravitational waves. General relativity has a century of rock-solid experimental evidence behind it, whereas the PV model is seen by many as a toy theory that's useful for intuition, but probably not a literal description of how the universe works. There have been claims of small amounts of thrust in devices like the EM drive or other asymmetric capacitor experiments, but so far none of these have survived the kind of rigorous independent verification needed to prove they're interacting with the vacuum and not just pushing off the air or reacting to heat.
Part 4, the legacy of thinking differently. Even with all those caveats, the pursuit of the polarizable vacuum model is incredibly valuable. It forces us to ask deep questions about the relationship between gravity, electromagnetism, and the quantum vacuum. We know that empty space isn't truly empty. It's filled with zero-point energy and virtual particles that pop in and out of existence. If we ever do figure out how to tap into that energy or manipulate those fluctuations, it will likely be because we took these radical ideas seriously and tried to bridge the gap between abstract geometry and practical engineering. Whether the PV model is the ultimate answer or just a stepping stone, it keeps the dream of interstellar travel alive. It suggests that the stars aren't unreachable, we just haven't learned how to sail the vacuum yet. It reminds us that every great leap in human history started with someone looking at nothing and seeing a way to move through it. The next time you look up at a clear night sky, don't think of it as a vast empty distance. Think of it as a medium, an ocean of potential, just waiting for the right kind of lens to focus its power. Maybe one day we'll build a ship that doesn't just travel through space, but learns to speak its language.
The air in the lecture hall at the University of Utah on March 23, 1989, was thick with more than just the hum of television cameras. It was charged with the kind of electricity that only accompanies a potential crack in the foundation of the world. Two chemists, Stanley Ponce and Martin Fleischmann, stood before a forest of microphones and made a claim that should have changed everything. They spoke of a simple tabletop experiment, palladium electrodes, heavy water, and a jar that had produced more energy than it consumed. They called it cold fusion. In that moment, the dream of limitless, clean energy seemed within reach. But within months, the dream was a crime scene. The scientific establishment didn't just disagree, they excommunicated. Papers were retracted, funding vanished, and the very term cold fusion became a career-killing epithet, a label of pathological science that served as a warning to anyone else who dared to look for a shortcut through the laws of physics. This moment created a ghost that still haunts the halls of research today. It established a modern blueprint for how institutional dogma defends its borders against the unknown. It's the backdrop against which every controversial breakthrough must now fight, including a radical vision of the universe known as the polarizable vacuum theory, or PV. To understand the barriers faced by theories like PV, you have to understand that science is not just a search for truth. It is an immense multi-billion-dollar infrastructure of peer review, federal grants, and tenure tracks, a system that, by its very design, treats a radical new idea not as a discovery, but as a contagion. Imagine standing in a quiet, sun-drenched lab in Austin, Texas. A physicist named Hal Puthoff is looking at a beam of light. To the rest of the world, following the gospel of Albert Einstein, that light bends because the space it travels through is curved, a literal dent in the fabric of four-dimensional spacetime. But Puthoff sees something else. He sees the polarizable vacuum. In the PV model, space isn't an abstract geometric shape. It's a medium, a substance with a density and a refractive index, much like glass or water. Puthoff's theory suggests that when light passes near a massive object like a star, it doesn't bend because of curved space. It bends because the vacuum itself has become polarized, its thickness changing in response to gravity. It is a subtle shift in perspective, but the implications are tectonic. If space is a medium, we might be able to engineer it. We might be able to change its refractive index, creating metric engineering that could lead to propellantless propulsion, or even the manipulation of time itself. But as Puthoff discovered, the distance between a working equation and a published paper is often guarded by a wall of high tensile silence. The first barrier isn't a lack of evidence, it's the language of the gatekeepers. In the world of theoretical physics, the Standard Model and general relativity are the high languages. To challenge them is to speak a dialect that many reviewers refuse to translate. When a scientist submits a paper on something as controversial as PV, they encounter the gatekeeping paradox. The peer review system, designed to filter out junk science, often acts as a filter for anything that threatens the reputational economy of the reviewers themselves. Think of the anonymous peer reviewer, often referred to as Reviewer 2 in academic folklore. This person is likely a senior scientist whose entire career, dozens of papers, and millions in funding are built on the very theory the newcomer is trying to dismantle. If the new theory is right, the reviewer's life's work becomes a historical footnote. The result is often a desk rejection, a brief email stating the work is not of interest to our readers or lacks a foundation in established literature. It is a polite way of saying the heresy will not be heard.
This isn't just a hurdle, it's a career death trap. Because in the modern university system, if you don't publish in the top-tier journals, you don't get tenure. And if you don't have tenure, you don't get to ask the dangerous questions. Beyond the journal editors lies the second, more formidable wall, the funding chasm. Most fundamental research in the United States and Europe is fueled by massive government agencies like the National Science Foundation or the Department of Energy. These agencies operate on a cycle of safe progress. When a funding committee sits down to distribute a limited pool of taxpayer money, they're looking for feasibility and preliminary data. This creates a closed loop. Money goes to researchers who are already working within the established paradigm because their outcomes are predictable. If you propose a study on string theory, a concept that has dominated physics for decades, despite having zero experimental evidence, the money flows easily. It is prestige research. But if you propose a study on the polarizable vacuum, a theory that suggests Einstein might have been looking at an effect rather than a cause, the committee sees a risk. They see fringe. They see another potential cold fusion embarrassment. The irony is that this conservative funding loop actually slows the very progress it's meant to accelerate. We spend billions on the Large Hadron Collider to find particles predicted 50 years ago, while leaving the radical outliers to survive on the scraps of private philanthropy. This has led to the rise of what some call the invisible college, or the breakaway labs. Places like EarthTech International, Puthoff's private research facility, represent a new model of science. Underfunded by the state and ignored by the mainstream journals, these researchers operate in a parallel world. They have their own conferences and their own journals, like Progress in Physics, where the barriers to entry are lower, but the stigma is higher. To the mainstream, these are the echo chambers of the fringe. To the researchers inside, they are the only places where the scientific method still allows for actual surprise. But there is a high cost to this isolation. When a theory like PV is forced into the shadows, it loses the corrective heat of the broader community. Without the rigorous, often brutal feedback of the mainstream, fringe theories can drift into speculation or pathological territory. The institutional wall doesn't just block progress, it creates a polarization of its own, where the establishment becomes dogmatic and the outsiders become defensive. We're left with a scientific landscape where breakthroughs often have to wait for what Max Planck famously called the funeral of the old guard. Planck observed that science doesn't necessarily advance by convincing its opponents, but rather because its opponents eventually die and a new generation grows up that is familiar with the new truth. But in an era of multi-generational projects and massive institutional inertia, can we afford to wait for the funerals? The struggle of the polarizable vacuum theory is a symptom of a deeper tension in human knowledge. It is the clash between the need for order, the dogma that keeps us from chasing every ghost, and the necessity of the radical leap. We have built a cathedral of science that is magnificent in its precision, but we have made the doors so heavy that the very people meant to expand it can no longer get inside. If we want to find the next paradigm shift, we may need to reconsider the red lines we've drawn around our funding and our journals. We may need to find a way to fund the outliers, not because they are definitely right, but because the history of science proves that the most important answers often come from the questions we were once afraid to ask.
March 23, 1989. Two men, Stanley Pons and Martin Fleischmann, stood before a wall of television cameras at the University of Utah. They weren't just claiming a discovery, They were promising an end to history as we knew it. In a simple glass jar using little more than heavy water and a rod of palladium, they claimed to have created nuclear fusion at room temperature. They called it cold fusion. The headlines the next day compared it to the discovery of fire. It was the Holy Grail, a way to power the entire planet for millions of years using nothing more than seawater. But within months, the dream collapsed. High-profile labs at MIT and Caltech tried to replicate the experiment and failed. The scientific community, fueled by a mixture of genuine skepticism and territorial protectionism from the hot fusion establishment, didn't just move on, they turned cold fusion into a synonym for pathological science. By late 1989, it was a joke, a cautionary tale taught to freshmen about the dangers of science by press release. But for a handful of researchers, the story didn't end with the ridicule. While the rest of the world looked away, a quiet underground of believers, though they would prefer the term experimentalists, refused to let the light go out. They saw things in those jars that couldn't be explained away as simple errors. They measured helium and tritium, the ash of nuclear reactions, in amounts that shouldn't have been there. This wasn't a group of cranks in garages. These were tenured professors and career government scientists who traded their reputations for a chance to chase a ghost that they were convinced was real. They rebranded the field as low-energy nuclear reactions, or LNER, attempting to strip away the stigma of the 1989 debacle. They spent decades working in the shadows, often funding their own research or relying on the quiet support of unconventional, deep-pocketed investors. One of the most pivotal figures in this quiet resistance was Michael McCube, a New Zealand-born electrochemist. He was the director of the Energy Research Center at SRI International in Menlo Park. He was a man of rigorous, almost obsessive methodology. After the 1989 announcement, he didn't just try to replicate the Utah experiment. He built a fortress around it. In his lab, experiments were conducted behind bulletproof glass. This wasn't just for safety, though a cold fusion cell had actually exploded in his lab in 1992, killing a collaborator and leaving McCube with glass shards embedded in his side. It was a metaphor for his stance against the scientific establishment. McCube spent nearly 40 years running over 150 long-term experiments. He was looking for the signal in the noise, specifically the correlation between excess heat and the production of helium-4. He didn't just want to see a temperature spike, he wanted to see the nuclear residue that proved fusion was happening. For decades, he served as the technical backbone of the community, a man who, until his passing in August 2025, insisted that the answer was hidden in the material itself. The technical challenge was staggering. The core of the Fleischmann-Pons effect relied on loading, forcing deuterium atoms into the crystalline lattice of a metal, usually palladium. Think of it like trying to pack a suitcase that's already full. As the concentration of deuterium increases, the atoms are jammed so tightly together that, according to LENR theory, they overcome their natural repulsion and fuse. Mainstream physics says this is impossible at room temperature because of the Coulomb barrier, the electrical force that keeps nuclei apart. To overcome it, you're supposed to need the heat of a star. But McCubre and his colleagues, like Peter Hagelstein at MIT, argued that something else was happening in the solid state. Hagelstein, an applied physicist who had once worked on X-ray lasers for the Star Wars missile defense program, developed complex Hamiltonian models suggesting that the energy from fusion could be dissipated into the metal lattice as vibrational energy, or phonons, rather than high-energy radiation. It was a radical idea, a nuclear reaction that didn't leave a radioactive smoking gun, but instead just got the metal hot. While McCube and Hagelstein fought the battle in the journals and at small, marginalized conferences, the field was eventually reinvigorated by a new kind of player, the environmentalist billionaire. Enter Tom Darden. Darden was the founder of Cherokee Investment Partners, a multi-billion-dollar private equity firm specializing in cleaning up contaminated industrial sites. He wasn't looking for a quick exit or a tech IPO. He was a no-exit investor, motivated by a sense of moral obligation to solve the pollution crisis. In 2012, Darden founded a subsidiary called Industrial Heat. He didn't just fund one lab. He set out to gather the most promising minds in the LENR space. For years, industrial heat operated in extreme secrecy, with its primary laboratory tucked away in an unremarkable facility in Cary, North Carolina. Darden was willing to be wrong, and he spent over $100 million to find out. His labs became a haven for researchers like Edmund Storms, a veteran nuclear chemist from Los Alamos who had been chasing cold fusion since the very first 1989 report.
The Cary lab wasn't just doing academic work, they were testing prototypes. Darden's team triaged dozens of different approaches to low-energy fusion. They looked at everything from the original electrolytic cells to nickel-hydrogen systems that used metallic nanopowders. The goal was commercialization, turning a scientific anomaly into a working industrial boiler. The stakes were enormous. If industrial heat could produce a device that generated megawatts of heat from a few grams of fuel, it would make fossil fuels and even traditional nuclear reactors obsolete overnight. But the road was treacherous. In 2014, industrial heat famously tangled with Andrea Rossi, an eccentric Italian inventor who claimed to have a working energy catalyzer, or ECAT. The relationship ended in a bitter multi-year legal battle that threatened to overshadow the genuine science being done in the background. Darden eventually moved on, stating that while the ECAT hadn't delivered, his confidence in the underlying physics of LNR remained unshaken. He shifted his focus to other, more rigorous avenues, funding a network of researchers including Mel Miles and Pamela Mosier-Boss, a scientist with the U.S. Navy who had reported seeing high-energy particle tracks in her own LNR experiments.
The turning point, the moment the cold case was officially reopened, came in the mid-2020s. The quiet persistence of the underground began to merge with the cutting edge of materials science and AI. In Japan, Clean Planet, a startup funded by giants like Mitsubishi and Nissan, began reporting consistent, 100% reproducible excess heat in their own reactors. They didn't use the cold fusion label. They called it quantum hydrogen energy. Their team, led by Yasuhiro Iwamura of Tohoku University, utilized nanostructured multi-layer films of nickel and copper. They weren't just guessing anymore. They were using AI tools to model the behavior of hydrogen atoms inside the metal lattice at the nanoscale. By 2025, Clean Planet was building a pilot plant in Kawasaki, aiming to mass-produce industrial heating modules by 2030. They had solved the reproducibility problem by treating the metal not as a passive host, but as a precision-engineered catalyst. Even the U.S. government, which had spent 35 years keeping cold fusion at arm's length, finally blinked. In 2023, the Department of Energy's Innovation Agency, ARPA-E, announced $10 million in funding for 8 different LNER projects. It was a fraction of the billions spent on hot fusion, but the symbolic victory was total. The agency's director, Evelyn Wang, explicitly stated that they wanted to break the knowledge impasse and find out, once and for all, if these anomalies were real. This led to the August 2025 publication of a groundbreaking paper in Nature. A team at the University of British Columbia, led by Curtis Berlinguet, described their Thunderbird reactor. It was a benchtop device that combined an electrochemical cell with a compact particle accelerator. For the first time in a top-tier mainstream journal, researchers showed that by squeezing deuterium into a palladium target with just 1 volt of electricity, they could boost fusion rates by 15%. It wasn't a net energy generator yet, but it was a demonstration of the core principle that Fleischmann and Pons had died defending, that chemistry can indeed influence nuclear physics. Today, the movement has moved beyond the believer phase and into the engineering phase. Private firms like Brilwin Energy in Berkeley and ENG8 in the UK are moving toward commercial-scale prototypes. They aren't looking for a single breakthrough. They are iterating on the materials, the pulse frequencies, and the catalysts. The legacy of 1989 has shifted from a story of fraud to a story of the reputation trap, a reminder of how easily scientific progress can be derailed by stigma. The researchers who stayed the course, who lost their lab spaces and their funding, are finally seeing their work validated by a new generation of scientists who don't remember the 1989 press conference. They are the architects of a silent revolution, working in places like Cary and Kawasaki to prove that the Holy Grail wasn't a delusion, it was just buried a little deeper than we first thought. The idea that empty space is actually a boiling sea of energy, a hidden reservoir of fluctuations reaching back to the dawn of time, sounds like something out of high-concept science fiction. But in 1989, a physicist named Hal Puthoff published a paper in Physical Review A that didn't just speculate on this energy, it proposed that gravity itself, the very force holding our feet to the ground and the planets in their orbits, is actually a byproduct of these quantum jitters. If we look at the universe through this lens, gravity isn't a fundamental, separate force of nature. Instead, it's an emergent effect, a kind of long-range residue of the electromagnetic zero-point field. This shifts the entire paradigm of physics, suggesting that what we perceive as mass and weight might actually be a complex interaction between matter and the vacuum.
It's a radical departure from the way we usually teach gravity. We're taught to think of it either as Newton's invisible tether or Einstein's curvature of spacetime. But Puthoff was building on a specific hypothesis proposed by Andrei Sakharov in 1967. Sakharov suggested that gravity might be an induced effect, much like the van der Waals forces that cause molecules to stick together. Puthoff took that conceptual seed and tried to build a rigorous quantitative model using what's called stochastic electrodynamics, or SED. In his view, if you have a charged particle sitting in the vacuum, it's not just sitting there. It's being constantly battered by these zero-point fluctuations of the electromagnetic field. This causes the particle to undergo a very high-frequency jittering motion known as Zitterbewegung. Puthoff argues that this internal kinetic energy is actually what we measure as the rest mass of the particle.
So, mass isn't an inherent property of the particle itself, but a measure of how much it's being pushed around by the vacuum? That feels like a complete inversion of the standard model. Usually we say a particle has mass, and therefore it feels gravity. Puthoff is saying the particle interacts with the vacuum, which creates the jitter, and that jitter manifests as mass. But how does that translate into an attractive force between two different objects? If I'm a jiggling particle and you're a jiggling particle, why do we move toward each other?
That's where the van der Waals analogy becomes critical. When these particles perform their Zitterbewegung, they essentially become tiny oscillating dipoles. Now, an oscillating dipole radiates its own secondary electromagnetic field. When you have two of these particles, their individual radiated fields interact with one another and with the background zero-point field. Puthoff's calculation shows that this interaction produces a net attractive force. Specifically, he identifies a long-range retarded van der Waals force. When he ran the numbers, he found that the leading term in his interaction potential perfectly matched Newton's inverse square law. What's truly striking is that he didn't have to plug in any arbitrary fudge factors to make it work. The gravitational constant g emerged naturally from the high-frequency cutoff of the zero-point spectrum, which is typically assumed to be around the Planck frequency.
It sounds mathematically elegant, but there's a significant tension here with general relativity. Einstein tells us that gravity is the geometry of space itself, the curving of the manifold. Puthoff's model is, at least in this 1989 paper, essentially a flat space theory. It treats gravity as a force moving through a pre-existing background. Can a theory that treats gravity as a simple electromagnetic residue actually account for things like time dilation or the bending of light around a star? Or is this just a clever way to replicate Newton's equations while missing the bigger picture of the curved universe?
That's a valid critique, and one that mainstream physicists have certainly hammered on. Puthoff's 1989 model is fundamentally a Newtonian approximation. It works beautifully for the low-energy, slow-velocity regime we experience in our daily lives. But general relativity isn't just about things falling, it's about the very structure of time and space. To address this, Puthoff later expanded his ideas into what he calls the polarizable vacuum, or PV model. In that framework, he suggests that the presence of matter doesn't just create a force, it actually alters the refractive index of the vacuum. It's as if mass changes the optical density of empty space, affecting the permittivity and permeability. This change in the vacuum's properties then dictates how light moves and how clocks run, mimicking the effects of curved spacetime. It's an attempt to provide a physical mechanism, an underlying medium for what Einstein described purely geometrically.
If we follow that logic, the curvature isn't a property of some abstract four-dimensional sheet, but a change in the physical density of the vacuum stuff around a massive object. It makes gravity feel much more like fluid dynamics or optics. But if gravity is just a variation of electromagnetism, why don't we see evidence of this connection more clearly? For example, the equivalence principle states that all objects fall at the same rate regardless of their composition. If gravity is an electromagnetic effect, shouldn't it depend on the specific charge-to-mass ratio of the material? A block of lead and a block of wood have very different internal electromagnetic structures.
Puthoff addresses this by drilling down to the level of partons, the subconstituents like quarks and electrons that make up all matter. He argues that because the zero-point fluctuations are universal and occur at such extremely high frequencies, every charged subparticle is responding to the vacuum in the same fundamental way. Since all matter is built from these same basic charged parts, the aggregate effect scales perfectly with the total amount of matter, regardless of whether it's lead or wood. In his derivation, the equivalence of inertial and gravitational mass isn't an accidental coincidence. It's a requirement of the model. The same zitterbang that gives a particle its inertia, its resistance to being moved, is the very same motion that generates the secondary fields causing gravitational attraction.
There's a persistent controversy regarding the math here, though. I've seen mentions of a 1993 response by Steve Carlip, who claimed that Puthoff's derivation contained a serious computational error. Carlip argued that if you actually carry out the integration correctly, the resulting force would be so incredibly small that it couldn't possibly account for gravity as we observe it. This seems like a fatal blow. If the numbers don't add up to the G we measure in the lab, the theory is just a nice story. How did Puthoff respond to that?
Puthoff's rebuttal centered on the parameters of the model, specifically the high-frequency cutoff and the nature of the particle-field coupling. He argued that by adjusting the assumptions about how particles interact with the highest frequencies of the vacuum, the force could be restored to observed levels. This is where the fringe label often comes in. Critics argued that if you have to constantly tune your parameters to match experimental reality, you're not predicting the force, you're just describing it after the fact. However, Puthoff supporters point out that the standard model of particle physics itself has dozens of arbitrary parameters that have to be measured and plugged in. They see his work as a pioneering attempt to find a more fundamental root for those numbers, even if the first-order math was subject to refinement.
It's also worth considering the historical context of the paper. It was published in Physical Review A, which is a top-tier, peer-reviewed journal. This wasn't some self-published manifesto. At the time, there was a genuine interest in exploring Sakharov's induced gravity idea because the search for a unified field theory was, and still is, hitting a wall. We have quantum mechanics for the small and general relativity for the large, and they don't talk to each other. Puthoff was essentially offering a bottom-up unification. If gravity is just high-frequency electromagnetism, you've unified the forces by simply showing that one is a subset of the other. It's an already unified theory, as he calls it.
Exactly, and that already unified aspect has huge implications for technology, which is what often gets people excited. If gravity is an electromagnetic phenomenon, then in principle, it should be possible to manipulate it using electromagnetic means. This is the seed of all that space-time metric engineering talk. If you could somehow shield an object from the zero-point fluctuations or alter the local energy density of the vacuum, you could theoretically reduce an object's inertial mass or create a repulsive effect. It moves the idea of a warp drive or propellantless propulsion from the realm of magic into the realm of extreme engineering. If you can change the permittivity of the vacuum around a craft, you're essentially changing the way gravity sees that craft.
But that brings us to the elephant in the room, the energy density itself. If the zero-point field is as energetic as these theories suggest, some calculations put it at 10 to the 110th power joules per cubic centimeter, why doesn't it blow the universe apart? Or more specifically, why doesn't its own mass equivalent create a gravitational field so strong that it collapses the entire cosmos into a singularity? This is the cosmological constant problem, and it's one of the biggest embarrassments in modern physics. Puthoff's theory seems to double down on this problem by making gravity dependent on that very energy.
That is the ultimate hurdle. In the Sakharov-Puthoff approach, the solution usually involves the idea that only changes or fluctuations in the vacuum energy density result in a net gravitational force. The uniform background sea of energy is essentially invisible because it's the same everywhere. It's like being deep underwater. You don't feel the weight of the ocean above you because the pressure is equal in all directions. It's only when you create a gradient, a difference in that pressure, that you get a force. In Puthoff's model, the presence of matter creates that gradient. But critics like Jack Sarfati have argued that this is too simplistic. They point out that in general relativity, energy density is a source of gravity, period. You can't just ignore the background. If the ZPF has the energy density Puthoff claims, the universe should be curved into a tiny ball. This remains a massive unresolved tension between SED-based models and the observed large-scale structure of the universe.
We also have to talk about the stochastic part of stochastic electrodynamics. This approach tries to explain quantum effects like the uncertainty principle as being caused by this random classical background field. It's a very realist view. It assumes there's a real field with real waves pushing things around. But the consensus in physics moved toward quantum electrodynamics, or QED, which treats these things using probability amplitudes and virtual particles. Is SED still considered a viable competitor, or is it more of a historical curiosity that Puthoff is trying to keep alive?
Most mainstream physicists would say QED won that battle decades ago. QED is arguably the most successful theory in the history of science, with predictions like the Lamb shift matching experiments to 10 decimal places. SED, on the other hand, works well for linear systems like the harmonic oscillator, but it struggles with nonlinear systems. It can't easily reproduce things like the hydrogen atom's ground state without some very clunky additions. However, there's a small, dedicated community of researchers who feel that the conceptual clarity of SED, the idea that there's an actual physical ether of fluctuations, is worth the mathematical struggle. They see it as a way to avoid the spooky non-locality and observer dependence of standard Copenhagen quantum mechanics. Puthoff is very much in that camp. He wants a universe that is mechanical and objective, even at the smallest scales.
It feels like Puthoff's paper is a bridge that never quite got finished. On one side, you have the beautiful Newtonian inverse square law emerging from the vacuum math. On the other side, you have the vast complex reality of general relativity and the high-precision successes of QED. Puthoff is trying to span that gap, but the bridge keeps shaking under the weight of things like the cosmological constant or the specific nuances of curved spacetime. Even so, the legacy of the paper is significant because it forced a conversation about the nothingness of space. It reminds us that the vacuum isn't just an empty stage where physics happens. It might be the lead actor.
That's the real takeaway. Whether Puthoff's specific equations for G are correct or not, the core insight that the vacuum is an active player in the gravitational game is actually becoming more mainstream, not less. Modern theories of emergent gravity from people like Eric Verlinde or the study of entanglement entropy as a source of gravity are all following a similar philosophical path. They're all trying to show that gravity is a macroscopic feeling of something much deeper and more chaotic happening at the quantum level. Puthoff was one of the few voices in the late 80s shouting this into a very skeptical room. He was looking for the why behind the how. Why is there a force between two masses? Because they're both swimming in the same energetic sea, and they can't help but be pushed together by the waves.
It's a vision of a deeply interconnected universe. If Puthoff is even partially right, then every time you drop a pen, it's falling because it's interacting with a field of energy that spans the entire cosmos. We aren't just objects sitting in space, we are dynamic patterns of energy, continuously exchanging momentum with the vacuum itself. It makes the mundane reality of weight feel like a profound cosmic dialogue. Even if the math needs a complete overhaul to satisfy the skeptics, that shift in perspective is incredibly powerful.
It really is. It turns gravity from a mystery we just accept into a puzzle we might eventually solve. If it's a force generated by fluctuations, then those fluctuations are something we can study, measure, and perhaps one day interact with directly. It's the ultimate high-stakes gamble in physics. If you're wrong, you've spent decades chasing a ghost in the vacuum, but if you're right, you've handed humanity the keys to the stars. The paper remains a landmark for its sheer audacity, challenging us to look at the nothing between the stars and see a source of infinite power and connection. This exploration of the hidden depths of empty space invites us to keep questioning the fundamental nature of our reality.
Physical Review A, Volume 39, Number 5, March 1st, 1989. Gravity as a Zero-Point Fluctuation Force. H. E. Puthoff. Institute for Advanced Studies at Austin, Texas, 78,746. Received March 14, 1988. Revised manuscript received August 15, 1988. Sakharov has proposed a suggestive model in which gravity is not a separately existing fundamental force, but rather an induced effect associated with zero-point fluctuations, ZPFs, of the vacuum, in much the same manner as the van der Waals and Casimir forces. In the spirit of this proposal, we develop a point particle, ZPF interaction model that accords with and fulfills this hypothesis. In the model, gravitational mass and its associated gravitational effects are shown to derive in a fully self-consistent way from electromagnetic ZPF-induced particle motion, Zitterbewegung. Because of its electromagnetic ZPF underpinning, gravitational theory in this form constitutes an already unified theory. Introduction. Gravitational theory, whether in its scalar Newtonian form or its tensor general relativistic form, is recognized to be essentially phenomenological in nature. As such, it invites attempts at derivation from a more fundamental set of underlying assumptions, and 6 such attempts are outlined in the standard reference book Gravitation by Misner, Thorne, and Wheeler, MTU. Of the 6 approaches presented in MTU, perhaps the most far-reaching in its implications for an underlying model is one due to Sakharov, namely, that gravitation is not a fundamental interaction at all, but rather an induced effect brought about by changes in the quantum fluctuation energy of the vacuum when matter is present. In this view, the attractive gravitational force is more akin to the induced van der Waals and Casimir forces than to the fundamental Coulomb force. Although speculative when first introduced by Sakharov in 1967, this hypothesis has led to a rich and ongoing literature on quantum fluctuation, induced gravity, that continues to be of interest. In this approach, the presence of matter in the vacuum is taken to constitute a kind of set of boundaries, as in a generalized Casimir effect, and the question of how quantum fluctuations of the vacuum under these circumstances can lead to an action and metric that reproduce Einstein gravity has been addressed from several viewpoints. These are treated in some detail in a comprehensive review by Adler on gravity, as a symmetry-breaking effect in quantum field theory. On the basis of heuristic and dimensional arguments along general relativistic lines, Sakharov argues that in a vacuum fluctuation model for gravity, the Newtonian gravitational constant g should be determined by an expression of the form g 11/2, where it corresponds to an effective Planck cutoff frequency of the vacuum zero-point fluctuation ZPF spec. Trum, in this approach, the small, but finite, value of the gravitational constant is an inverse reflection of the high, but not infinite, value of the high-frequency cutoff of the ZPF. In this paper we explore the Sakharov viewpoint on the basis of a conceptually simple classical model, but including ZPF, in which matter, in the form of charged point particles, partons, interacts with the ZPF of the vacuum electromagnetic field. As part of this development, the model predicts 1. To be precisely of the form G equal to WdAg. In order to constitute a self-consistent viable basis for gravitation, however, a first-order ZPF model for gravity must provide not only a basis for calculation of the gravitational constant G, shown to reflect the ZPF cutoff, but must also account for the genesis of the gravitational mass and the attractive inverse square law force. In the particular version of the Sakharov hypothesis pursued here, the mass is shown to correspond to the kinetic energy of ZPF-induced internal particle, parton, motion, ZPF jitter, or Zitterbewegung, while the force is found to be of a long-range retarded van der Waals type, associated with the broad-spectrum ZPF radiation fields generated by that same Zitterbewegung motion. To arrive at the above results, basically, we simply assemble together in a straightforward fashion previously published results regarding ZPF models of van der Waals and related effects in flat space-time. When this is done, one finds the leading term in the interaction potential, previously unexamined, to be Newton's law with no free parameters to be fixed. In such a fashion, the identification of this term as gravitational emerges naturally from the concatenation of the previously published results. Yet further evidence for the correctness of this interpretation is provided in SEC. 6. Where details of the pattern that emerges are presented in the context of a self-consistent, coherent picture of the underlying dynamics of the gravitational force that conforms to the facts as we know them. 39,333. 1989, The American Physical Society. 2,334. 39. Second vacuum ZPF electromagnetic fields, Ref 8. In the classical approach used here, point-particle, ZPF interactions are treated on the basis that charged point-mass particles interact with a background of random classical electromagnetic zero-point radiation with energy spectrum, as in the quantum mechanical case. P, W, dW2 hectares, or do2, where the first factor in parentheses corresponds to the density of normal modes, the second to an average energy per mode. This treatment of quantum field particle interactions on the basis of a classical ZPF constitutes an analysis technique known in the literature as stochastic electrodynamics, SED. SED is a well-defined framework that has a long history of success in yielding precise quantitative agreement with full QED treatments of such topics as Casimir 10-12 and van der Waals forces, topics directly related to the one pursued here. In this approach appears in the above expression simply in the role of scale factor, without need of quantum interpretation, and all other appearances of in the development can be traced back to its appearance in this expression. The spectral energy density represented by 3 formally diverges as W3. It is generally assumed, however, that the spectrum is effectively cut off at a frequency roughly corresponding to the Planck frequency. As we shall see in the following sections, this assumption is supported by the line of development presented here. As a first step toward developing the hypothesized underlying ZPF basis of the gravitational interaction, we compare the forms of the spectral distribution of the ZPF of the electromagnetic fields as seen from unaccelerated and accelerated frames of reference. Of particular significance with regard to the spectral distribution in an unaccelerated frame, given by 3, is the fact of its Lorentz invariance, which derives specifically from the spectrum's cubic dependence on frequency. The cubic spectrum is unique in its property that delicate cancellations of Doppler shifts with velocity boosts leaves the spectrum Lorentz invariant. 4. In an accelerated frame, on the other hand, the detailed balance of Doppler shift cancellations is negated, with the result that the spectral distribution takes the form 15. 2 PLO do equal to 1 plus C plus 2 KHXP, 2 RCO, A minus 1, where A is the proper acceleration relative to a Lorentz frame. This expression was originally derived by Boyers on the basis of the random classical ZPF background assumed here. The purpose was to derive a result, first obtained by Davies and Unruh within the context of quantum field theory, which showed that, apart from an additional density of states factor, 1 plus, the spectral distribution seen by an accelerating observer assumes a thermal Planck form if one makes the identification T equal to He, 2 MCA, K is Boltzmann's constant, T, absolute temperature. In commenting on the additional density of states factor, Boyer points out that the additional contribution beyond the thermal Planck form is related to the space-time properties of an accelerating reference frame. This gives us a clue that, via the equivalence principle, this additional term can be related to the gravitational interaction. Of special interest here, therefore, is not the thermal term of interest in the original treatment, but rather the leading terms. P, W polar, plus AP, W equal to plus. These indicate that an accelerated observer would see the background ZPF spectrum augmented by a term proportional to the square of the acceleration. Application of the principle of equivalence then indicates that the additional spectral contribution seen in a frame with acceleration A should also be seen in a non-accelerated frame with local gravitational field 8, produced by a gravitational mass m setting G equal to S-1 gm R2 we obtain AP equal to 225 gmg. Thus, the principle of equivalence predicts an additional contribution to ZPF energy by gravitational mass, a requirement that must be met in any ZPF-based theory of gravitation. Since this additional contribution of energy is electromagnetic in nature, we must ascribe to mass an appropriate electromagnetic field-generating function, a point to which we return in SEC. Fourth third, Zitterbewegung model. As our basic point, particle, ZPF interaction model, we represent matter as a collection of charged point mass particles, partons, in accordance with standard theory. In the development that follows it, is not necessary to invoke the details of particular parton representations, for example, families of fractionally charged quarks, beyond certain general concepts, such as the asymptotic freedom of partons to respond to the high-frequency components of the ZPF spectrum as essentially free particles. It is necessary to focus to the charged parton level, however, in order to represent properly the essentially equal magnitudes of proton and neutron contributions to gravitational mass. This accounts for the fact that charged and neutral matter participate equally in the gravitational interaction based on underlying charged parton interactions. We begin our discussion of particle field interactions by examining the properties of a simple charged harmonic oscillator of natural frequency A, corresponding to a binding force that is linear in displacement from equilibrium, located at the origin and immersed in 0 point. 39. Gravity as a zero-point fluctuation force. 2335. Radiation. The non-relativistic equation of motion for a particle of mass μ and charge q, including radiation damping, is given by μ plus mor. If we introduce the dipole moment, P equal to qr, and the damping constant, R equal to q2, Bromok 3, we can write 7 in a form convenient for later discussion. P plus Wp equal to Tb plus 6 ReC3 TeZp. We will also be particularly interested in the kinetic energy, MOT, which becomes 12TeC3R. Once written in this form, the oscillator equation of motion, 8, and energy equation, 9, refer only to the global properties of the oscillator, dipole moment P, natural frequency, and damping constant I, and do not involve individual mechanical properties of the oscillator such as charge or mass. With regard to the ZPF fields, the vacuum is assumed to be filled with a random classical zero-point electromagnetic radiation, whose Fourier composition underlies the spectrum given in 3. Written as a sum over plane waves, the random radiation, which is homogeneous, isotropic, and Lorentz invariant, can be expressed as 2 Espia T equal to ReZD 3 key 11 halves, 11 halves HP, R, T, RED 3K, X2, 1 to 0 840 XL, X plus 1, K, where 1, 2 denote orthogonal polarizations and are orthogonal unit vectors in the direction of the electric field polarization and wave propagation vectors, respectively, K, are random phases distributed uniformly on the interval 0 to 2, independently distributed for each K, O, and A. It is at this point that we need to consider the correspondence between the above equations and the parton, ZPF interaction of interest. First, we treat the parton as a 2-dimensional rather than 3-dimensional oscillator, drawing on previous studies that model spin as the internal angular momentum associated with 2-dimensional Zitterbewegung motion. Second, because we are interested primarily in the particle's high-frequency Zitterbewegung response to the ZPF, whose spectral density increases as a 3, we may to first order neglect the binding force term involving WO, asymptotic freedom, as it relates to the ZPF. Finally, we also neglect the radiation damping force in comparison to the inertial force and ZPF driving terms. Alternatively, the restoring force and radiation damping terms can be carried through in the derivations that follow, and appropriate approximations introduced at the end, without change of result. To obtain the expectation value of kinetic energy of the Zitterbewegung motion given by 9, 6, p. 12 μ, we follow a procedure due to Rueda. Under the asymptotically free particle assumptions stated in the paragraph above, the x component of 8 takes the form with a unit vector in the x direction. dp, h is 11 halves equal to 6 13 t, ezp equal to 6 3 rd 3k 2 to 2 dt. Integrating once with respect to time, we obtain px6 rec, retfd 3k 2 to 2 equal to 6 me, red 3k. 11, 2 to 10. The expectation value p then follows from 1 half 11 halves has who, 8 euros, iw xp, ik, r plus I0, k, o minus 10. Conjugates and the notate stems from the use of exponential notation. Equation 14 can, however, be simplified to P2 equal to 363 deg 3, D3K 82821, psi 821, where averaging over random phases involves the use of exp I K2, R plus 10 K A 0K equal to 883 KT, with dk dk dkk2 and the angular integration in K taking the form equal to FDN 1 K2 3 equal to 4. We can rewrite 15 with a change of variables to key as 2 equal to 1263 r to 1 cos 12 firsts plus a cost 7 sin a r. Where is the assumed cutoff frequency to be determined later? 21 4 p reaches the value for the two-dimensional Zitterbewegung motion assumed p2 equal to O2, p2 equal to 12 euros 3r22, which when substituted into 9 yields 6 go 21. It is thus seen that the expectation value of the kinetic energy of Parton's Zitterbewegung motion reaches a finite magnitude, limited by the finite value of the, as yet undetermined, ZPF cutoff frequency. The energy calculated in this way is in the nature of the so-called transverse self-energy, in QED, of a particle in response to the electromagnetic zero-point fluctuations of the vacuum. Since the energy associated with this Zitterbewegung motion is an internal particle energy, that is, not directly observable, we identify this energy as that corresponding to the rest mass energy of the particle, m equal to 6 gon 22, as will be shown in SEC 4W, Me3, G12, in which case 22 reduces to GeG 23. In this view, the particle mass m is of dynamical origin. Originating in Parton, motion responds to the electromagnetic zero-point fluctuations of the vacuum. It is therefore simply a special case of the general proposition that the internal kinetic energy of a system contributes to the effective mass of that system. This derivation of mass as an internal kinetic energy of motion is thus the first result derived from the Zitterbewegung model. As will be shown in later sections, it is this mass that is involved in the gravitational interaction. Fourth, Zitterbewegung fields. We turn our attention now to the fields generated by the ZPF-induced Zitterbewegung motion. Considering, say, the x component of motion, we find that an assumed E time dependence substituted into 8 yields for the magnitude of any particular frequency component. P0 equal to xp, where the overtilt designates the magnitude of a frequency component, and once again we have neglected the binding and radiation damping forces. This expression can then be combined with the ZPF field expressions, 10 and 11, and the standard oscillating dipole formulas, EW re alpha p epsilon rho, GP, 1, A, equal to re B4, to yield expressions for the dipole fields generated by the Zitterbewegung motion, viz. E, re sigma alpha kappa 4 euros H, re 4.5 11 halves, plus, where, with a unit vector, in the direction joining the dipole to the field evaluation point, 39. Gravity as a zero-point fluctuation force, 2337, 1 plus, 32 P2 minus 2, Kr 3 Kr 2 degrees Fahrenheit equal to Kx I plus Kr2. The energy density in the dipole field distribution can be calculated from 27 and 28 as Awa equal to E, greater than plus H2, 12.2, equal to Re alpha piomicron, 11.2.5 Fes, S4 dead, to 10 times, or G or 3xp, plus 10, K, O minus 10, K. 2012 Fu 86011 halves or 12 He, 8x, 2 to 2, 2 to 2, F2xp, A, plus 10, K, minus 10, K. This reduces to Ogmda, or F or 2 plus or G or 2, 3 R 16 square meters, deg 20, where we have made use of 17 and have averaged over random phases by the use of xp, A, plus 10, K, O, minus 10, K. 888 kk. The part of the integrand in parentheses in 32 can be evaluated by means of 29 and 30 and yields 2 sin Kr 2 plus 4 cos 4 sos 2 plus sin 2 Kr. Kr, where is the angle measured from the dipole motion unit vector to the evaluation point unit vector? The first term proportional to 1/2 constitutes the radiation field associated with the ZPF-driven dipole. As shown previously by Boyer, this radiation just replaces that being absorbed from the background on a detailed balance basis with regard to both frequency and angular distribution, and therefore does not result in an incremental change to the background. Of the two remaining, induction, field terms, the one, R term predominates at large distances and is therefore the one of interest here. Designating the term of interest by a prime, we have 3Cl2 Cos2 4 square meters deltioto micron SWW. This expression, obtained on the basis of considering a single x component of motion, must be doubled to take into account the contributions of the two independent degrees of freedom in the model. This leads then to an overall spectral density, a paler, equal to 24. Since in the final analysis we are interested in the net contribution of a large collection of randomly oriented individual particle motions, we average over the solid angle to obtain Apple, AP2R sine 22, since according to 22 there is a relationship between I and the particle mass m for ZPF-driven Zitterbewegung motion, 37, can also be written. APGLA equal to 2. Zitterbewegung motion therefore leads to the generation of an electromagnetic field distribution in proximity to the mass that is proportional to frequency times mass squared, divided by r, and upon detailed examination is found to be half electric, half magnetic. According to 6, moreover, a field of just this form is required by the principle of equivalence. Under the assumption that the gravitational and rest masses are identical, m equal to m, 6, and 38, can be equated to obtain the cutoff frequency, 11 halves r, which satisfies the Sakharov condition, 1, in terms of the cutoff frequency, we, 39, can be inverted to yield the gravitational constant g in the form of the second, non-independent Sakharov condition, namely TT2. We see, therefore, that the principle of equivalence requires a certain modification of the ZPF background by gravitational mass, and that the Zitterbewegung model of mass implies a similar modification. Furthermore, the compatibility of the two conditions on a precise quantitative basis requires only the equivalence of gravitational. 2338. H. E. Puthoff. 39. And rest masses, and a limiting cutoff frequency for the ZPF background on the order of the Planck frequency. This specification of the cutoff frequency W2 and its relationship to the gravitational constant g is thus the second result derived from the Zitterbewegung model. Thus we have a derivation that yields the relationships postulated to exist in dynamical scale invariance breaking models of gravity as a symmetry breaking effect. Fifth, gravitational force. The derivations in SECs. 3 and 4 dealt essentially with the characteristics of single masses. In this section we investigate the interaction between two such masses. The starting point is equations of the form 8, written for two masses, but modified to take into account the fact that each mass experiences not only the background ZPF field, but also the ZPF-driven dipole field of the other mass. The procedure followed here is precisely that developed by Boyer for the derivation of the retarded van der Waals forces at all distances between a pair of polarizable particles. Therefore, we need only outline the procedure as it applies to our case. Two masses A and B, taken here to be equal for ease of discussion, are assumed to be located at positions ρ Tg, respectively, with B located a distance r from A, along the positive z-axis of a coordinate system centered at A. The equations of motion, generalized from 8, take the form plus 6 euros 3 TE 1 plus 6 3 TE 1 1, where ERT is the dipole electric field at the position of particle A due to the motion of particle B, and so forth. As in the derivations of previous sections, an assumed Elliott time dependence yields, for the magnitude of any particular frequency component, equations of the form D plus P equal to 6 euros 1 C3 T EZR, WRG, and similar equations for the Y and Z components where D equal to W2 plus 2 IGW3, 1I1 plus KR, KR, KR3, I1 plus KR2, KR3. The latter expressions for N, etc., are derived for the geometry under consideration from the dipole expressions 25 and 29, consistent with the assumptions of previous sections. We neglect the binding and radiation damping terms in and I in 45. Furthermore, on the scale of interest in gravitation, distance is large compared with the wavelengths of the predominant Zitterbewegung frequencies. In calculating the force, we retain only the radiation field term 1, Kr. With these assumptions, 45, 47 become DRAD 2, Kr 0. Solutions for X and Pax are obtained straightforwardly from 43 and 44, subject to the conditions 48 and 49. It is then necessary to construct from these solutions the appropriate van der Waals forces between the pair of particles A and B. From classical theory, the force on a dipole is given by F equal to PV E plus PXB dP dt. Following Boyer, we note that the time-averaged force can be transformed as dP F equal to PVE plus DXB dt equal to PVE plus PX VXC, where the transformation of the second term, PXB equal to XBdR, follows from an integration by parts and substitution from Maxwell's equations, noting that the endpoint terms do not contribute to the time average. Manipulation of the vector operators in 51 then leads to the relatively compact form F equal to PV plus PV plus PV. One further reduction is possible. The symmetry of the geometry dictates that the average force on a dipole is along the z-axis joining the two particles. Therefore, the expression for the average force finally simplifies to F equal to F2 equal to P2 equal to AX as plus P2 plus pi as G as. In determining the average force on, say, dipole B, we must keep in mind that the electric field at B consists of both the background ZPF field and the dipole field due to particle 4, so that, for example, the first term in 54 becomes Pax RT equal to Pax Es 1 plus P, and so forth. The mathematics of carrying out the averaging then proceeds term by term, as in Ref 27, using, as in previous sections, the RE and complex conjugate notation. 39. Gravity as a zero-point fluctuation force. 2339, including averaging over random phases. The result for the special case of interest here, radiation field only, binding and radiation damping forces neglected, is in terms of the potential U29. Do 2 rands. The only difference here as compared to the derivation in Ref 27, aside from the specialization to the radiation field term, is the use of a finite cutoff frequency. This result is derived here and in Ref 27, on the basis of point particles interacting with a classical zero-point field. For those who might be more familiar with standard quantum calculations, this result has also been obtained by Renner from quantum electrodynamic calculations using a non-relativistic quantum oscillator model, and by Casimir and Polder using fourth-order perturbation theory in quantum electrodynamics. Equation 56 was derived for the case in which 3 degrees of freedom for particle motion are assumed. For the two-dimensional Zitterbewegung motion assumed in our case, n equal to 2, geometrical considerations require that u be reduced by a factor, n32, see Appendix A. With this taken into account, the solution 56 becomes u21, cos 29, r322 sin r, where y equal to w1rr equal to c, with the potential thus defined, the force is obtained from F equal to OR. We see therefore that the potential has the desired one. R dependence required for gravity, modulated by a fine structure overlay of the form sin R, 2, which has a spatial periodicity characteristic of the cutoff, Planck, frequency, 10 to 3 cm. If we extract the leading, non-oscillatory term, we find for the potential and force U equal to tar F equal to plus equal to 2 rands. A careful examination of the details of averaging over the rapid spatial variation, see Appendix B, indicates that the particle experiences an average force, F, given by the leading term in 61, with R given by 23, and A by 39, F can then be written in Newton's law form with no adjustable parameters required, F, gm2r2. This derivation of Newton's law, which expresses gravity as a van der Waals force, is thus the third and final result derived from the Zitterbewegung model. Sixth discussion. We begin our discussion by reiterating the logic flow of the approach pursued here. The basic thesis is the Sakharov proposal that gravity is not a separately existing fundamental force, but rather a residuum force derived from zero-point fluctuations of other fields, in the manner of the Casimir and van der Waals forces. Particularizing this hypothesis to the ZPF of the vacuum electromagnetic field, we identify the gravitational force as the van der Waals force associated with the long-range radiation fields, as opposed to the usual shorter-range induction fields generated by the Zitterbewegung particle, parton, motion response to the ZPF of the electromagnetic field. The steps in this identification are 3. First, particle mass is defined as the internal, that is, unobserved kinetic energy of Zitterbewegung motion. Its value is set by a radiation, damping constant I intrinsic to the particle, in conjunction with the value of the universal cutoff frequency. Second, the value of the cutoff frequency is determined by the equivalence principle. This principle sets a requirement that an expected additional contribution to the free space Lorentz frame ZPF spectrum, viewed from an accelerated frame, is to be equated to a similar contribution expected in an unaccelerated frame, but in a gravitational field, that is, near a particle performing Zitterbewegung motion, and thereby generating a mass term. Third, a straightforward calculation of the long-range van der Waals force associated with the radiation field, correlated motions of such particles, whose parameters are determined by the above 2 steps, leads to Newton's law with no free parameters to be fixed. With a detailed theory in hand, certain attributes of the gravitational interaction become explicable in fundamental terms. As mentioned earlier, the relative weakness of the gravitational force is due to the fact that the coupling constant determined by 40 g me3h reflects as the inverse square the high value of the ZPF cutoff frequency. With regard to the attractive nature of the force, this is simply a reflection of a property typical of van der Waals forces in general. The fact that gravitational interaction is characterized by a unipolar, single-valued charge, mass, can be traced to a, positive only, kinetic energy basis for the mass parameter. The lack of shielding effects in gravity can also be comprehended on a rational basis. As understood here, this is a consequence of the fact that ZPF noise, quantum noise, in general cannot be shielded, a factor which in other contexts sets a lower limit on the detectability of electromagnetic signals. Specifically, in the case of ordinary electromagnetic shielding, macroscopic materials constitute dense boundaries that substantially alter field distributions, with shielding one consequence. In the gravitational case as modelled here, however, matter constitutes a dilute particle gas in an essentially high-frequency Hohlraum. As a result, particles ZPF interact. 2340. H. E. Puthoff. 39. Chance have negligible effect on the overall field distribution, hence a lack of shielding, while nonetheless permitting particle-particle interactions that lead to an attractive potential. In addition, implicit in the development pursued here are issues that extend beyond the gravitational interaction, such as mass renormalization and possible ZPF-induced contributions to the binding forces within the nucleus. However, of the many inferences that can be drawn from this study, the most important is simply the fact that it is possible to carry through the basic Sakharov program, namely, to uncover a basis for gravity in the ZPF of other non-gravitational fields. In particular, we have been able to explicate a first-order model 32 based on the ZPF of the vacuum electromagnetic field alone, once we take into account its effects on particle motion. The model thus details an electromagnetic basis for gravity. Assuming the model is a proper representation of the gravitational interaction, the already unified aspect of the model would seem to mitigate against canonical attempts at unification of gravity as a separate force, or quantization of gravity as a separate field, in favor of a viewpoint more aligned with that presented here. It is therefore seen that a well-defined, precise, quantitative argument can be made that gravity is a form of long-range van der Waals force associated with particle Zitterbewegung response to the zero-point fluctuations of the electromagnetic field. As such, the gravitational interaction takes its place alongside the short-range van der Waals forces and the Casimir force as related phenomena which emerge from the underlying dynamics of the interaction of particles with the zero-point fluctuations of the vacuum electromagnetic field. Acknowledgements. I wish to express my appreciation to Professor H. Yilmaz for encouragement and useful discussion regarding the pursuit of ZPF concepts. I also wish to thank Professor Arueda of the University of Puerto Rico for helpful correspondence and for providing useful reference materials on early ZPF studies. Finally, I am indebted to G.W. Church Jr. for invaluable collaborative discussion throughout this effort. Appendix A, Dimensional Reduction Factor for Coupling Constant. As discussed in SEC. 5. The attractive force between particles derives from coupling between ZPF-induced dipole motions of the particles involved. The nature of the coupling is simplified somewhat in that the coupling takes place only between corresponding components of the motions of the two particles, that is, between and PBX-PA and PA and PA and P. This can be seen in the form taken by 43 and 44, in the derivation which leads to expression 56 for the interaction potential U, reference to the original derivation in Ref 27, shows that the potential is proportional to the quantity, plus 3 plus 2, where n, etc., are as given here in 46 and 47. That derivation assumes full three-dimensional motion, with a coupling to Pax P2, pay, and as to by. For the two-dimensional Zitterbewegung motions posited here, however, we may for convenience analyze the couplings on the basis of assuming a random distribution of 1/3 each of x-oriented dipoles, yz motion, y-oriented dipoles, xz motion, and z-oriented dipoles, xy motion. For two x-oriented dipoles, both y and z motions couple, yielding a contribution proportional to plus for an x-oriented dipole, pz motion, coupling to a y-oriented dipole, xz motion, only the z components couple, leading to a contribution proportional to, and so forth. For the 9 possible dipole pair combinations, straightforward enumeration of the possibilities leads to an average coupling factor proportional to 4 square meters plus 4 plus 4 square meters, and equal to 4 n2 plus n2 plus m2. As a result, for the two-dimensional motions of interest here, a reduction factor of is to be applied to the value of the coupling constant obtained for the general three-dimensional case without constraints. Appendix B, Average Force. In the Zitterbewegung model of gravity, the two-particle interaction potential based on the radiation field van der Waals effect is given by 57 repeated here. U equal to -21. Cos, 2 rands, R32 Cinia RR, as seen, This expression can be factored into two parts, one with a slow spatial variation, 1 r, and one with a rapid spatial variation, on the order of the Planck wavelength. Sin r of interest in the gravitational interaction is not the rapidly varying component, but rather an average value, averaged over a distance large compared to the Planck wavelength. With the potential given by B1, the normalized force is given by J equal to R2 AR1, cos2 R3. As particle separation changes by an amount r, the corresponding change in potential is given by O R plus AR FDR plus AR1 cos2 rands Dr. RR31 cos2 rands R plus cos2 R plus AR R plus AR 3 B3. Assuming integration over a full cycle of the Planck variation so that cos 2 R plus AR equal to CO's 2 rands, and recognizing that AR, so that R plus AR equal to R plus 3 Ra, we find that B3 simplifies to 2R39, gravity as a zero-point fluctuation force. 2341, the change in potential, integrated over a cycle, is seen from B4 to be sensitive to where in the cycle, 0 to R1, the integration was begun. The average change in potential is therefore determined by averaging over the range of possible initial starting points within the cycle, namely n less than or equal to n plus 1, where n is an integer n. By reference to standard tables of integrals, we find, using B4 equal to YR2 1 rand plus 1, 2YR, 2 COs, 2 rands, 3 plus sin, 2R, SOS, 2 rands, 2R, 2R plus 2 rands plus 3x3, 5x, plus 1. Substitution of the limits of integration, with the recognition that n greater than 1 implies that n plus 1 equal to n3 plus pn then leads to O, Ya2yr, tn2, 2, 2, 3, 2, plus pe 31, 51. But the term in large parentheses is recognized to be sin, 2 times equal to 0, so that Au becomes OU, Ya R2, from which the average force can be calculated as F R RR2, F equal to 7 equal to #re. C.W. Misner, K.S. Thorne, and J. O. Wheeler, Gravitation, Freeman, San Francisco, 1973, pp. 417 to 428. 2 degrees Celsius. W. Misner, K.S. Thorne, and J. O. Wheeler, Ref. 1, pp. 426 to 428. 3 A.D. Sakharov, Dokal, Akkad, Naux SSR, SOV, Phys, Dokal 12, 1040, 1968. These include the following. Sakharov's own conjecture that the Lagrange function of the gravitational field is generated by vacuum polarization effects due to fermions. A.D. Sakharov, Theo, Math. Phys. 23,435, 1975. The generation of gravity as a collective excitation of fermion-antifermion pairs. Kayakama, Ichikashige, Tematsuki, and H. Terazawa. Prog. Theo. Phys. 60, 868, 1978. Proof that curvature can arise from the quantum fluctuations of pure gauge fields. B. Haslacher and E. Motolo. Phys. Let 95 billions 237th 1980. The generation of gravity as a symmetry-breaking effect in quantum field theory, in which a dynamical scale invariance breaking is postulated to take place at energies near the Planck mass. A Z. Phys. Reverend Let. 42, 417, 1979. Phys. Reverend D. 23858, 1981. Pregeometric models in which the Einstein action and metric are generated from quantum fluctuations of matter fields. Diamati and G. Veneziano Phys. Let. 105 billions 358, 1981. S. Yoshimoto, Prog. Theo. Phys. 78,435, 1987. 5 seconds. Adler, Reverend Mod. Phys. 54,729, 1982. In this review, particular emphasis is placed on the case of renormalizable field theories with dynamical scale invariance breaking, in which the induced gravitational effective action is finite and calculable. In the terminology of gravity as a symmetry breaking effect, equations of this form are an immediate consequence of a postulated dynamical scale invariance breaking that is assumed to take place near the Planck mass energy. For details, see a Z, Ref 4. In the sense that gravity as a non-Minkowskian curvature effect can be treated in first approximation as a Newtonian force in flat spacetime, so can it be treated as a van der Waals type force in flat spacetime. And it is this basic concept that is addressed here. Although beyond the intended scope of this paper, an intimate connection between flat spacetime van der Waals and Casimir effects and vacuum curvature effects can be traced as a problem in the restructuring of vacuum energy, as in B. S. DeWitt, Phys. Rep. 19,295, 1975, especially pp. 303 to 308. Thus the connection between a flat space-time approach and gravity as a curvature effect can be established as in general relativity generally. Although the approach taken here is to assume the reality of the ZPF of the electromagnetic field, for completeness we note that an alternative viewpoint posits that the results of field-particle interactions traditionally attributed to ZPF can also be expressed in terms of the radiation reaction of the particles involved, without explicit reference to the ZPF. See P. W. Maloney, in Foundations of Radiation Theory and Quantum Electrodynamics, edited by a Oberut, Plenum, New York, 1980, Phys. Reverend a 25, 1315, 1982. The interrelationship between these two approaches, ZPF, radiation reaction, can be shown to be complementary on the basis of an 2342, H. E. Puthoff. 39. Underlying fluctuation dissipation theorem. For further discussion of the SED approach, see, for example, H. E. Puthoff, Phys. Reverend D. 35, 3266, 1987, and references therein. Specifically, for a detailed description of the correspondence between this approach and QD treatments of linear dipoles plus radiation field systems, see P. W. Maloney, Phys. Rep. 25, 1, 1976, especially AP 71 to 78. See also reviews of SAD by T. H. Boyer in Foundations of Radiation Theory and Quantum Electrodynamics, edited by a Oberut, Plenum, New York, 1980, L. de la Peña, in Proceedings of the Latin American School of Physics, Cali, Columbia, 1982, edited by B. Gomez et al., World Scientific, Singapore, 1983. 10 E. M. Lifshitz, J. X. Pav. It, too, Phys. J. 1953, 1956. It W. Marshall. Nuovo, Cimento, 38,206, 1965. 12. T. H. Boyer, Phys. Reverend D. 11,790, 1975. 13 trillions. H. Boyer, Phys. Reverend of 5, 1799, 1972. 6. 314, 1972. 7. 1,832, 1973. 9. 2,078, 1975. 11. 1,650, 1975. T. H. Boyer, Phys. Reverend 182, 1,374, 1969. 15. T. H. Boyer, Phys. Reverend D. 21st, 2,137, 1980. See also J. S. Kim, K. S. So, S. K. Kim, and J. H. Yi, Phys. Reverend D. 36, 3,700, 1987, 16 P. C. W. Davies, J. Phys. A. 8, 609, 1975, 17 W. G. Unruh, Phys. Reverend D. 14,870, 1976, 18 in a later paper. T. H. Boyer, Phys. Reverend D. 29, 1089, 1984. Boyer shows that under the usual low-frequency peaked resonance approximation, the additional density of states factor cancels out, with the result that to this order of approximation gravitational effects are neglected. As will be shown in SEC. 3, however, it is in the emergence of high-to-frequency behavior, where the additional density of states factor remains operative, that gravitational effects have their origin. 19 K. Huang, M. J. Phys. 20,479, 1952. 20 A. Rueda, Phys. Reverend February 23, 2020, 1981. 2. The possible existence of a cutoff in quantum theory is recognized to introduce a non-Lorentz invariant factor in that detection of a Doppler-shifted cutoff frequency by a moving detector, in principle, reveal absolute motion. As pointed out in the literature, however, for example, by M. Ashoup, A.M., J. Phys. 53, 122, 1985. As long as the cutoff frequency is beyond detectability, as is the Planck frequency in this case, there is no measurable consequence expected of such a breakdown of Lorentz invariance at this limit of present physical theory, either now or in the foreseeable future. 22. See, for example, W. Heitler, The Quantum Theory of Radiation, 3rd ed., Oxford University Press, London, 1954. pp. 293, f. 23. Bohm, The Special Theory of Relativity, Benjamin Cummings, Reading, Ma, 1965, chap 1924. The particle mass given by 23 equal to Re3 corresponds to a renormalized or dressed mass, and it is this mass, of dynamical origin, that appears in the field, generation effects, and interaction potential corresponding to gravity. If one wished to do so, the derivation that led to 23 would permit one to extract an unobserved harmonic oscillator bare mass μ, which appears in the definition of I preceding, 8. This unrenormalized mass is given by the large value μ, M, where MP, Hc, G is the Planck mass. Although unobserved experimentally, it is this unrenormalized mass O which could be said to interact at the level of the ZPF. Viewed in the usual QED terms, its value is so high and its Compton wavelength so small as to justify its treatment as a point particle, as we have done, even at wavelengths corresponding to the ZPF, Planck, cutoff frequency. Lacking any apparent dynamic origin or interaction effects at an observable level, however, the concept of a bare mass can be seen to be simply an inference derived from the particle parameter 1, which appears to be the operative parameter of significance. Therefore, questions as to why the bare mass does not generate a large gravitational field, which can be taken to be related to the well-known field-theoretic conundrum as to why the vacuum zero-point energy does not do likewise, find a simple solution in the Sakharov approach, as pursued here. In the dynamics of the model, the only gravitational fields found to emerge from the analysis are those that are in fact observed experimentally, and this is one of the strengths of the approach. 25. See, for example, J. A. Stratton, Electromagnetic Theory, M.C. Graw-Hill, New York, 1941, p. 435. 26. C. T. H. Boyer, Ref. 12. Appendix B27, Trillions. H. Boyer, Phys. Reverend 7, 1832, 1973, 28 trillions. H. Boyer, Ref. 27, EQs, and 57, 29. The complete expression, including both radiation and induction field terms, is given by 92 in Ref. 27. It is, in our units, and for W20, 9 U redu R3 do I56 plus HR WR33 R. This constitutes the general expression for the retarded van der Waals forces at all distances. While the first, radiation field, term in large parentheses, is found here to account for the long-range gravitational interaction, The remaining short-range, induction field, terms have yet to be investigated with regard to their contribution to binding at the nuclear, parton, and nucleon level. J. Wren, 53,193, 1971. 30 millions Physica, 3 hours. B. G. D. Polder, Phys. Reverend 73,360, 1948. Casimir and 32, further development of the model could include, for example, extending Parton-Zitterbewegung to the relativistic case. 33. See, for example, H. B. Dwight, Tables of Integrals and Other Mathematical Data, Macmillan, New York, 1961, especially E's. 441.14 and 431.11.